Hi, my name is Steven. Welcome to this little behind the scenes video where I take you through some of the steps that I took to make this little 4-bit adder project. Firstly, we need to decide on a transistor. I decided that the project will run off a 5V source, and from there, I also wanted to make it very low power, which is why I decided on the popular 3904 NPN BJT. Now that we have that, we need to figure out how to turn it on. So at a high level, BJTs turn on by supplying enough current to the base, which then allow current to flow from the collector to the emitter. There also exists saturation, where the relationship between current and voltage allows us to achieve very predictable results. From the datasheet, we can see that this voltage, VCE, is 0.2 volts, when the current at the collector is 10 milliamps and the current at the base is 1 milliamp. From this knowledge, we know we need to limit the current into collector and base, which is where we get this very simple schematic. From there, we use Ohm's law to calculate R2, which ends up around 4.8K from the math shown on the screen. The closest standard value we have is 4.7K, so we take a bit of error here. Don't worry, we'll correct that later, I'll get to that. We then use the current gain, or beta, to calculate the current we'll actually need to get at the base. This again comes from the datasheet, where we use the worst case beta in this calculation, which is 100. From the math, we get around 0.1 milliamps. Finally, using this logic, we can apply Ohm's law again to get our R1 value, which is 43K. 43.2K is the closest that we have and that I can find cheaply on DigiKey, so we'll use that instead. Perfect! And after building it out, we can see from the multimeter that it does in fact turn on. As a matter of fact, we just made our first logic gate, a NOT gate. Speaking of logic gates, we need to design and build a few of them for this project. We come up with the designs for an AND, OR, and NAND gates. Combining these, we also get the design for an XOR gate, which we'll need later. So why do we need these logic gates? Let's take a look at what we actually want to do. To add two numbers, we need to take two inputs and an output as an answer, obviously, as well as a possible carryout, because sometimes when you add numbers, there is going to be a carryover. Now how do we do this? So we know in binary addition 0 plus 0 equals 0, 1 plus 0 equals 1, and the other way around, and 1 plus 1 equals 2, which is represented in binary by 1, 0. By this, we need the following truth table, with the carryout 1 ignored for now. This looks a lot like the truth table for an XOR gate. Now we take care of the carryout, which is only high if both inputs are 1. This truth table looks a lot like an AND gate. Now let's add those to the design. We are now finished with the design for the first digit, and now we have a little 1-bit adder. From here, we replace the gates with their respective transistor level circuit, which looks a little bit like this, and there we have it. Now for the second digit onwards, we will always have 3 inputs instead of 2, a carry and the 2 inputs, and we want to output a carry and a solution. To spare the time, the logic gate level design is here, and the transistor level design by the same logic is here. Now just a note, remember how we had to use resistors that aren't exactly what we wanted? Since the carryout signal is being used throughout the entire circuit, we need to make sure that the voltage drops aren't propagating across the entire thing, and that each digit always gets a fresh 5V carryout input signal. As a result, every layer we need to run it through an op-amp, in which I chose the LM358. Since we want a non-inverting amp here, we use the schematic for that and the equation for that to calculate the required resistance values. The math for the first layer and the upper layers are slightly different, and they're shown on the screen here. Okay, so that's it. From there, I tested everything and went to work with Altium designing it out. To keep it small, I decided to use SMD components for this project as well. Here's the circuit for the first layer, the upper layers, and the control boards. I manufactured the first layer and the control board at home since they were pretty simple. For the upper layers, I wanted to keep them nice and small, so I decided to design it as a double-side PCB and order them from overseas. Finally, with everything connected, the project is complete. I really hope everything made sense and wasn't super boring, but I had a lot of fun using some of the stuff I learned as an engineering student in the classroom in real applications. Thank you for watching this video, and hopefully I'll see you soon.